Professor Davis back with you as we move into section 7.3, titled Measures of Centrality. So let's go ahead and set this up. In the first two sections, we talked about this notion of graphical descriptive statistics, where we talked about the idea of Pareto charts, histograms, and frequency polygons that gave us an idea of a sample of data using a picture. And now we want to turn our attention to the other branch of descriptive statistics called numerical descriptive statistics. So this involves having special numbers which give us an idea of the shape and dispersion and center of a sample of data. So this idea with the measures of centrality give us an idea of what the typical data item would look like in a sample. So there are several of these measures. Let's go ahead and get at them here. The first one I think you all know, you've seen this before, the most common statistical measure, the mean, sometimes called the arithmetic mean, or the average would be the colloquial term. So we can say for a sample of n data items, the sample mean is given by, here it is, x bar, x, that's how that's read. That's the symbol for sample mean. And what is it? It's the sum of the data items divided by the sample size, all right? In other words, the number of data items we have. Written mathematically, that would be the first data item. I call that x sub 1, the second data item x sub 2, and so on, up to the nth data item, which I called x sub n, divided by the number of data items we have. In other words, the sample size. Now, if the sample is regarded as a population, then we compute the population mean. And take a look at it. It's really the same formula, it's just the notation is different. For population parameters, we typically use Greek letters. This is the Greek letter mu, all right? And we take the sum of the data items divided by the population size, and notice we denote that with a large capital letter N, all right? So we'll be primarily focused on the sample mean. So let's take a look at an example and see how we can compute the sample mean. The 9 largest oil reserves measured in billions of barrels by country in 2000 are shown in the table here. Let's determine the sample mean and interpret the solution. All right, so let me grab my calculator. And what we want to do is to be able to compute these numerical descriptive statistics, sometimes called summary statistics, compute all of these using our calculator, all right, without having to rely on every formula, because this formula is very simple. Some of them later on, not so much. So to do that, I'm going to click on the Stat button, and then right here at Edit, at Option 1, I'm going to go ahead and hit number 1, and there you get something that looks like a spreadsheet, and I'm just going to go ahead and type in these 9 numbers. And there we have the last number put in of 29. All right, so we have all our numbers put in here. Now to compute the sample mean, we'll hit the Stat button one more time, and then cursor right over to the Calc menu and pick the very first option that says 1 variable stats. All right, that's opposed to 2 variable stats you could use like for linear regression models and that kind of thing. So I just hit Option 1 and hit Enter because the data is in list number 1. And there we get our output. Notice the very first item is X bar 92.2. So it looks like that's our sample mean. Let's go ahead and verify that. So remember what we did. Hit Stat and selected 1 to edit and enter the data in list 1. Then press Stat, scroll over to the Calc menu and select 1 variable stats. And we get the sample mean. So we can interpret that by saying that this means that in 2000, the reserves of the top 9 countries with the largest oil reserve averaged about 97.7 million barrels. I guess that's 92.2 billion barrels. So there we have that. Now, let's kind of expand things out just a little bit here. And let's see what happens. Let's tie together what we talked about back in section 7.2 to this idea of the mean, and talking about approximating the mean from a given frequency distribution. In other words, a grouped frequency distribution. So for data that's been summarized in a grouped frequency distribution, we can approximate the mean by the following formula. Here it is. So the mean would be the sum of the midpoints, x sub m, all right, times the corresponding frequency of the class, and then we take the sum of those products, that's what the sigma sign is for, and we divide that by the sum of the frequencies, the sample size. Let's just summarize here. X sub m is the midpoint of each class, f is the class frequency, and n is the sample size, in other words, the sum of the frequencies. So let's go ahead and try an example and see if we can approximate the mean from a given grouped frequency distribution. So consider this data. The ages of U.S. prisoners sentenced to death in 1980 is shown in the table. Determine the mean of the frequency distribution and interpret the result. So the first thing we'd want to do is to determine the midpoint of each class. So I'll go ahead and do the first one here. Let me clear out the stuff we were doing before. I'll hit the second key and then the mode key to quit, and then we can hit clear. So we'll just take 15 plus 24 and then divide that by 2 using our midpoint formula. And so we get 19.5. That is the midpoint of the first class. Now, I don't think we need to use our calculator to get the class width. Look, 25 minus 15, that's 10. 35 minus 25, that's 10. So the class width is 10. So we can just successively add 10 to get the remaining class midpoint. So the midpoint of the second class would be 29.5, and then 39.5, and so on. And then we want to multiply those midpoints by the class frequencies. Let's see what we get here. So here are those 5 class midpoints that we were talking about. And then we want to multiply that midpoint times the frequency of the class. So for the first class, 19.5 times 184, we get 3,588. 29.5 times 334 gives us 9,853, and so on for the remaining 3 classes. And now, notice the product is given in the right-hand column. Okay, so let's go ahead and compute the sum of the frequencies to get the sample size. We'll have 184 plus 334 plus 144 plus 42 plus 10. And so it looks like we get 714 for that. So we'll go ahead and verify that result. There it is, 714. And then finally, we have to do this long calculation. So think of what that's going to be here. Here, I'll go ahead and get things started. We're going to take 19.5, the midpoint of the first class, add that to this product over here from the second column, 3,588 plus 29.5 times 9,853 plus 39.5 times 5,688, almost done, plus 49.5 times 2,079, and then finally we want to add on 59.5 times 595, and then we want to divide that by that sum of the frequencies, the sample size. That was 714. So let me show you what you get. There's all those calculations. So we end up with 30.54. So let's go ahead and interpret that solution now. This means that in 1980, the approximate age of prisoners sentenced to death was about 30.54 years of age. So that's how we can approximate the mean of data that's already been summarized in a frequency distribution. So let's get back to looking at some of the other measures of centrality here. We talked about the mean. I guess the next natural one to talk about would be the median. We can say for a set of data, the median, denoted by the letter M, is the middle value of the sample data after it's been ranked from smallest to largest. Now, a couple notes on the median. One of the advantages that the median has over the mean is that the median is resistant to outliers. And by that, I mean a data item that's a whole lot different than all the other data items. All right? So it resists being thrown off by these outliers because you're throwing out the high and low until you get to the middle. Now, if the sample size is an even number, well, we have a little calculation to do. We'll rank the data from least to greatest, find the two middle numbers, and then the median will be the mean of those two middle numbers. So let's take a look at an example and see how we compute the median. The top news, information, and entertainment websites from May of 2000 is shown in the table. Let's compute the median and interpret the answer here. All right? So let's see here. I don't think this is going to be that hard. It looks like the data is already ranked. These are the top information websites. So it looks like the sample size is what? 1, 2, 3, 4, 5, 6. All right. So it looks like our median will be the mean of these two middle data items. Remember, they've already been ranked from least to greatest. So let me get my calculator. Let's go ahead and do that now. So we'll take the third data item, 9.4, add that to 8.9, divide that by 2. We have two data items there, so we get 9.15. All right, so the data is already sorted. There it is. And we want the mean of the two middle data items, and we get 9.15. So this means that in May 2000, the median number of visitors to the top news, information, and entertainment websites was 9.15 million users. All right? So that's the second of our primary measures of centrality. Let's talk about the third one now, the mode. The mode's interesting. It has some rather unique properties. We can say for a set of data, either categorical or qualitative, the mode, denoted by M sub 0, that's read M naught, is the data item or data items that have the highest frequency. Now, a couple of things about the mode here. First, if no data items are repeated, then the data simply has no mode, and that's how we would report the answer. If more than one data item has the highest frequency, then each of those data items is the mode. So we can have more than one answer. See, that's two distinctions between the mean and the median, and then the mode. All right? The mean and the median, their existence is guaranteed. Not so with the mode if none of the data items repeat. Given a set of data, you can only compute one mean, and you can only compute one median. That's different than the mode, which can have more than one answer. So let's take a look at an example here. The 9 largest oil reserves, measured in billions of barrels by country in 2000, are shown in the table. Find the mode and interpret. Well, notice here, the data is already sorted for us, so that's good. That makes it easier to look at, all right? And it looks like none of the numbers repeat here until we get to the very bottom, right? We have 229s for Libya and Mexico. So, from inspecting the data, we see that the data item 29 occurs with the highest frequency of 2, so that is the mode. Not the frequency, but the data item which yields that highest frequency. So the frequency here is 29, And so we can interpret that by saying this means that the most frequently occurring amount of oil reserves in the data was 29 million barrels. So we've talked about the mean, the median, and the mode, and how to approximate the mean for data which has already been summarized in a frequency distribution. Now there's one more measure of center, maybe you've never heard of, but it's a very nice measure of center to use if you're only given limited information. And that's called the mid-range. So let's go ahead and define it here. We can say for a set of data, the mid-range, denoted by MR, is given by, so what do we do here? We take the minimum data value, add that to the maximum data value, and divide that sum by 2. Now a couple of notes on the mid-range here. First, since the mid-range uses the largest and smallest values, by definition, it's susceptible to those outliers that I talked about earlier. All right? So the median can be easily thrown off by outliers. Second, I call the mid-range the measure of center of least resort. This is the measure of center you want to use if you're only given the minimum and maximum values. So let's go ahead and try one of these and compute the mid-range here. The top 15 countries in internet usage in 1998 is shown in the table. Let's determine the mid-range. Well, notice here, this data, fortunately for us, is ranked from least to greatest, so it's going to be pretty easy to get the mid-range here. We'll just take the maximum data value of 76, add that to the smallest data value, that's Finland down there, 1.6, divide that by 2. And so we get what? 38.8. All right? So let's go ahead and verify that answer. So there's our mid-range, 38.8. And we can interpret that by saying that this means that the mid-range of the top 15 countries in internet usage in 1998 was 38.8 million. All right? So those are our 4 measures of centrality: the mean, the median, the mode, and the mid-range. And we also talked about computing the approximating the mean for a given grouped frequency distribution. Now, one more thing I want to talk about in this section here, and that's about this notion of skewness and symmetry. First off, we can say that if the middle classes of a histogram have the highest frequency and the other classes are a mirror image about that middle, we call the distribution symmetric. So you've probably seen this kind of thing before. It's also called triangular shaped. It's also called bell shaped. All right? And so it doesn't have to be exactly the same on each class going down like this, but we're just saying in terms of the general shape. So in the case of a symmetric distribution, the mean and the median are approximately equal. So notice here I wrote x bar and m, all right? So in the case of a symmetric distribution, the mean and the median will always be approximately equal. Contrast that with something like this. Now, if the higher frequencies occur in the lower or beginning classes, pardon me, then we say the distribution is skewed to the right. There it is right there. There's an example of a distribution that's skewed right. So in the case of a distribution with right skewness, that means the mean is greater than the median. So notice here, think of this as the number line. Here's the mean. It's to the right of the median, so it must be a bigger number. So by saying skewed right, we mean that data tails off to the right. A lot of times people get this idea of skewness exactly backwards. Skewness isn't where the bulk of the data is, it's where the data tails off. And conversely, we can say if the higher frequencies occur in the upper or latter classes, we say the distribution is skewed left. So there is a picture of a distribution that's skewed left. All right? Notice here, it tails off to the left. All right? If a distribution is skewed to the left, in that case the median is bigger than the mean. So notice, take a look here, I've plotted the mean and the median on this histogram, and here's the mean. The median is to the right of that, so it must be the bigger number. So again, the skewness is determined by where the graph tails off and not where the bulk of the data is. So let's take a look at an example here. How about this? The ages of U.S. prisoners sentenced to death, we've already seen this, is shown in the table. Determine if the distribution is generally skewed left, skewed right, or symmetric. Well, I went ahead and made a histogram of this data. Let me show it to you. There it is right there. And you see here, the data starts out here. The most frequent class is the second class, and then it tails off to the right. All right? So here's an example of data which is skewed to the right. All right? In other words, it tails off to the right. So that takes care of the notion of symmetry and skewness of distributions, and that takes care of measures of centrality.